Hello Year 12, welcome to the 6th video here for trig functions. We are looking at applications of differentiation today. Now we looked at differentiating the derivative of trig functions in our last video. And now we are going to look at applications of these. These are things like tangents, normals and curve sketching. Rightio, we've done lots of these sorts of things before and we're not going to apply anything particularly new to it. Right, same old ideas, right, just with slightly different applications now that we have a trig function in there instead. Now, without too much more mucking around, I want to get straight into the example here because the sketching tends to take a long time. Okay, it tends to take a long time. We are going to... Where those 7s and 12s come from? Oh dear. Right, so... let's get straight into this. Sorry about the distractions there. Right, we're going to go through the same process as we normally would. We have an equation here. So in this case, y equals sine x plus cos x over the domain 0 to 2 pi. So first of all, right, step 1, endpoints. All right, what is the y of 0? Equals sine 0 plus cos 0, oops, not cos theta, just get in the habit of doing that, cos 0 equals, alright, sine 0, we need to remember some of these, 0 plus 1 equals 1. Also, the y of 2 pi, same thing, right, equals sine of 2 pi plus the cos of 2 pi. Equals 0 plus 1 equals 1. Okay, there are our two endpoints. So I know that's where it starts and finishes at 1 and 1. Next thing that we're going to do is find our intercepts. Now, well, I suppose we've got our vertical intercept. We're going to find some x-intercepts, and there could be a few. 2 intercepts. Let y equal 0, that'll give us any x-intercepts. Therefore, sine x plus cos x equals 0. Therefore, sine x is equal to negative cos x. Right, this is a little tricky to solve. Here. Maybe it's going to help us to... we kind of need to know some of our values, apply a certain amount of common sense and whatever else, x and y. Now we know that they're the positive things here. Well, first of all, when is sine x equal to cos x? Right, well, it's when the opposite on adjacent is equal to the... opposite on hypotenuse is equal to the adjacent on hypotenuse. So that really tells me it's when the opposite is equal to the adjacent. Yep. Right, when we have pi on 4. Yeah, I get 1, 1 and root 2. Right, the sine of pi over 4 is 1 over root 2. The cos is 1 over root 2. So, for sine and cos to be equal in magnitude but opposite in direction, right, here, right, in the first quadrant, sine and cos are equal, same sign. Here they're going to be different, so that's one of my options there, right? Which is going to be, this is going to be pi over 2. That's a full pi, so this is 3 pi over 4. So x equals 3 pi over 4. Okay, so 1 pi over 4, 2 pi over 4, 3 pi over 4. That's one option. Now tan, they would both be negative here, so it's not here. Over here, only cos is positive, right, so they're opposite here. Right, so you know that sine of 3 pi over 4 is going to be 1 over root 2. Cos of 3 pi over 4, right, is negative 1 over root 2. So they're sort of equal but opposite. So that's one option. Down here, which is going to be 1, 2, 3, 4, 5, 6, 7. 7 pi over 4, again, the sine of 7 pi on 4, right, is going to be negative 1 over root 2. The cos of 7 pi over 4 is 1 over root 2. So they're sort of equal but opposite. Now, there's not going to be any more. So 3 over 4 pi, 7 over 4 pi, no more intercepts. So I've got 2 x-intercepts. Wonderful. Now, the next thing that we're going to do here is to differentiate to find any stationary points. I'm just going to rule a line across there. 3 stationary points. So, differentiate my function. Y prime equals, right, differential of sine is cos, and the differential of cos is negative sine x. Right, yeah. So I've got this thing. Now what I need to do is I need to find the zeros of this. I want to know when my gradient is equal to 0, because they're going to be my sort of horizontal or stationary points. Let y prime equals 0. Therefore, cos x minus sine x equals 0. Therefore, cos x equals sine x. When does cos x equal sine x? Well, in fact, it's going to be here and here. So I'm just going to sort of jump the gun a little bit here, and I'm going to say x equals pi over 4 and what's this? 1, 2, 3, 4, 5 pi over 4. Right, 2 solutions there. So I've got my endpoints, right? At the start, it's at 1. The end, it finishes at 1 again. I have my my x-intercepts at 3 pi over 4 and 7 pi over 4. I have some stationary points here and here, but let's do a little bit more with these. I'm going to use up a lot of space here. In fact, I'm going to have to find some more. So now I'm going to say the y of pi over 4. Right, substitute pi over 4 into my original thing is the sine of pi over 4 plus the cos of pi over 4, which equals 1 on root 2 plus 1 on root 2, which equals 2 over root 2, multiply top and bottom by root 2, and I get 2 root 2 over 2, which just equals root 2. Right, you can go back and check the thirds if you like, but that is going to be the value there. So now I have a coordinate there. Right, I have, right, my curve passes through the point pi over 4 root 2. Now let's have a look at this other one here where x equals 5 pi over 4. Y of 5 pi over 4. Now this is a little bit trickier. You've got to do these angles of any magnitude again. You sort of reminds you why we did it in the first place. But the sine of 5 pi over 4, right, over here, right, both sine and cos are negative there because tan is positive in the third quadrant. So this is negative 1 over root 2 minus 1 over root 2 equals, we worked it out, negative root 2. Righto. So I've got some more points here. I've got the start, I've got the end, I've got 2 intercepts, I've got 2 stationary points, the coordinates there. Now we really should work out the nature of those stationary points, and I prefer to do these with a second derivative. Textbook prefers to use a table of values and have a look at what's going on either side. I would rather look at the second derivative at those points to see if it is positive or negative, right? So now I'm just going to write, I just need to sort of quarantine that there, say for nature of stationary points. Okay, so y double prime equals, right? And particularly in this case here, it's not very difficult to find the second derivative of this, right? So the derivative of cos is negative sine x. The derivative of negative sine is negative cos x. Okay, so I've got this thing here. Now I want to find y double prime of pi over 4 equals, right, the sine of pi over 4, 1 over root 2. So I get negative 1 over root 2 minus 1 over root 2. Oh, is this right? Yeah, that's 1 over root 2 equals, I don't know why that 7's doing there, equals negative root 2, just the same as it does down here. Okay, so that's one of them. And y double prime, oh, in fact, maybe let's make this statement here. Therefore, right, that's a negative, so I have a local maximum, right? That means it's doing this, right, like that. Therefore, I have a local max at, right, stop that, at pi over 4 root 2. There's a maximum. Now I need to check this other one here. I'm going to say y double prime of pi over 4, but 5 pi over 4, that's my other one. Y double prime of 5 pi over 4 is equal to, right, remember 5 pi over 4, they're both negative here. Right, we've done pi over 4. They're both negative here, so it would be, it's negative, negative, so they become positives, okay? Because it's, so the sine of 5 pi over 4, right, this is what we're doing here, the sine of 5 pi over 4 would be negative 1 over root 2, and I've got the negative of negative, so that's 1 over root 2 plus 1 over root 2 equals root 2. Again, slow it down, check it. You'll find similar workings on other parts of this. You find with these trig functions there's a lot of similar calculations that keep coming out. So this tells me that's positive. So that's a local minimum, right? It's doing this sort of stuff. And I have a local minimum at 5 pi over 4 root negative root 2. Okay, negative root 2 here. Negative root 2 here. Negative root 2. Now, I think the one more thing that we should do here to be thorough, right, for step 5 is look for points of inflection. Points of inflection. So I'm going to say y double prime of 0. No, not the y double prime of 0. No, I want my second derivative equals to 0. Therefore, negative sine x minus cos x equals 0, which is the same as sine x plus cos x equals 0. We've already done that. When does sine x plus cos x equal 0? Y equals 0. Sine x plus cos x equals 0 are these ones here. So my points of inflection are the same as my x-intercepts. Right. And look, that's pretty typical on sine and cos curves. So now what I need to do is find some space. Find some space to draw this sketch. I'm going to have to run over to the side here. You're going to have to put it somewhere else. Sorry about that. Now I know that, you know what I'm going to do? Is I like to draw my curve first. You know that, and then put my axes in and mark the things off. But let's just say that I don't know exactly what it's going to look like yet. So let's draw some axes, do it roughly. Right? We'll do a sketch of a sketch, and then we'll draw a nice sketch afterwards. So x, y. Now it's obviously 0. Let's make this 2 pi here. Let's say it's pi here. This is going to be my pi over 2, pi over 4. Sorry, 3 pi over 4. Pi over 4. It's going to be my 3 pi over 2, 5 pi over 4, 7 pi over 4, there like that. We have maximums at root 2 and minimums at negative root 2. Now I know that I start here at 1. I have a maximum here. I have a maximum, is that right? And then I have a 0 at, where are my zeros at? 3 pi over 4. Oh, what's happened? Oh, you're kidding me, I've shut it down. Sorry. Cleaning up. This is a disaster. I'm sorry. Hang on. No, we're back. Okay, so it's got to come down through here to have a minimum here. Right, a minimum here, another 0, an inflection here, and I finish up. Right, I finish up here at 1 again. So in fact, can we sort of see that what happens is I go up and then down and around and up again. Right. Oh look, maybe that's good enough sketch. Right, you know that I would prefer to do this. And then put my axes in. It's open there, that's open there. This happens at 3 pi over 4. This is 1. Root 2. Oops, that should be, that happens pretty early. That's pi over 4. This is 5 pi over 4. 5 pi over 4. My points of inflection are at these zeros anyway, that's fine. That's at 1 there as well. Yeah, we should be able to see that. And this one here is negative root 2. Y-axis, my y-axis shouldn't be labelled there. It should be labelled here. This is, as you can see, a monster video now, but it's a big question to do. There's a lot to be done there, and I want to recap that if we are doing curve sketching, because you don't explicitly get told this on your formula sheet, you've got to remember it. Curve sketching, find the value at the endpoints, find the zeros, find the intercepts. Right, often that's done by factorising, but not here. So differentiate your function and find the horizontal points, the stationary points. Right, substitute the x value, so that'll give you the x value of the stationary point. Substitute that in to find the y value of that stationary point as well, back into your original function. Right, find the second derivative to determine, and then substituting the x values of your stationary points. That determines the nature of those stationary points, whether they are maxima, minima, or horizontal points of inflection. Let your second derivative equal 0 to find any other points of inflection. You can, somewhere along the line, right, early on in the piece, if it looks like it might be relevant, check for odd and even functions. Right? That sometimes it is, but not in this case here. So you sort of use your own judgment there as to whether or not that's relevant. Rightio. So there are lots of parts of this video. It's hit 20 minutes now. That should be stacks. I'll see you in class.